Welcome to the GATE Graduate Aptitude Test in Engineering, the subject called Electronic Devices. This is Dr. T. Thirupal, Professor in Electronics and Communication Engineering from G. Pullaiah College of Engineering and Technology, Kurnool. As we have seen in the last topics, different semiconductor physics topics where the structure of an atom and how does current flows, what for silicon is used, and also the mass action law, and different topics we have seen and also some problems we have solved. Let us continue the same topic what we have stopped in yesterday. So here in yesterday class we have stopped at the mass action law and we have also already dealt with the mass action law where it's nothing but a product of concentration of electrons and concentration of holes is a constant which is equal to Ni square. From this we can able to find the minority charge carrier concentration in the device. That is, suppose if it is n-type semiconductor, we can able to find the minority charge carrier concentration which is nothing but holes. That is, Nn can be written as donor concentration into Pn, that is equal to Ni square. So therefore, the minority charge carrier concentration in n-type is given by Ni square divided by Nd. So this is a minority charge carrier concentration in n-type. Similarly, we can able to find the minority charge carrier concentration in p-type. That is, Np into Pp is equal to Ni square. So therefore, Np into Pp can be written as acceptor concentration, that is equal to Ni square. So therefore, I can write this one as the minority charge carrier concentration electrons in p-type semiconductor is given by Ni square divided by Na. So we can able to find using mass action law the minority charge carrier concentration present in p-type and also in n-type semiconductors. And also I can say that one important topic point here, the semiconductor is always a neutral one, For example, if you take a semiconductor here, it may be a p-type semiconductor or n-type semiconductor, it is always a neutral one. For example, here majority charge carriers are electrons and therefore donor concentrations are present here. So therefore, here the total number of charge is donor concentration plus P. And whereas here a hole is present in p-type semiconductor majority charge carriers and an acceptor ion will be there here. So therefore, I can write this one as acceptor ion plus N. So therefore, the total charge which is nothing but acceptor ion plus N is equal to Nd plus P. So this is we can say that the semiconductor is a neutral one. The amount of charge in p-type semiconductor is equal to amount of charge in n-type semiconductor. So I can say that the semiconductor is nothing but a neutral one. A semiconductor is a neutral one. Okay. Now let us deal with some problems regarding mass action law. The first problem. Check this problem. Due to illumination by light, the electrons and hole concentrations in a heavily doped n-type semiconductor increases by delta n and delta p respectively. If Ni is intrinsic carrier concentration, then the options are given delta n less than delta p, B delta n greater than delta p, C delta n is equal to delta p, D delta n into delta p is equal to Ni square. So here, as illumination is been happened, the electrons and holes concentration in a heavily doped n-type semiconductor. In a heavily doped, it is given as n-type semiconductor. That too it is heavily doped, right? Increases by delta n and delta p. That means electrons, if you assume n, it is increased by n plus delta n, and holes p, it has been increased by p plus delta p. So the increment is given by delta n and delta p respectively. So if Ni is an intrinsic carrier concentration, then I can say that the equal amount of increment between electrons and holes is been happened. That is, delta n is equal to delta p. An equal amount of increment is been happened for holes and electrons. So this is what the answer for this question. Next, let us see the next gate question, which is in a P-type silicon sample, the whole concentration is 2.25 into 10 power 15 centimeter cube. That means P-type semiconductor is given and its whole concentration is given. P-type semiconductor whole concentration 2.25 into 10 power 15 centimeter cube, and if the intrinsic carrier concentration is 1.5, Ni is given as 1.5 into 10 power 10 per centimeter cube, then the electron concentration is, as we know that here we need to find the electron concentration N. So how to do this? It's a very simple. According to mass action law, we know that N into P is equal to Ni square. So N we need to find, that is equal to Ni square divided by P. So N is equal to Ni square 1.5 square into 10 power 10 into 2 10 power 20 divided by P, which is nothing but 2.25 into 10 power 15. So 1.5 square is 2.25, 2.25 gets cancelled, that is equal to 10 power 5 per centimeter cube. So therefore C is the right answer. Concentration of electrons is equal to 10 power 5 per centimeter cube. Next, the next topic, let us go the enhancement to the topic what we have learnt in previous classes. Next, the enhancement topic is called drift current. Drift current. What is drift current? Here we will learn about what is drift current, what tends for drift current to flow from one point to another point, right? So first of all, if you want to learn about the drift current, first you need to learn about first 2 points. The first point is you need to take a uniformly doped semiconductor. A uniformly doped semiconductor. If you want to generate a drift current, first you need to take a uniformly doped semiconductor, and second one, external electric field should be applied. External electric field should be applied. You need to apply external electric field to the device, right? So first, uniformly doped semiconductor you need to take, then you need to apply external electric field. So let us observe how does drift current flows. So I am taking here a P-type semiconductor where the majority charge carriers are holes. So here this is a P-type semiconductor and majority charge carriers are hole and they are uniformly doped. For example, see here, it is uniformly doped from this point to this point. 3 charge carriers are doped. From this point to this point, again 3 charge carriers. From this point to this point, again 3 charge carriers are doped. So this is what called as a uniformly doped concentration in a device, which is nothing but a semiconductor. So these are all called as a holes where majority charge carriers are holes in P-type semiconductor. This is a hole, 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 hole, hole and hole. Now, we need to make sure current has to flow from this point, starting point to ending point. So how does current starts to flow from starting point to ending point here? So for this, all holes has to move from starting point to ending point. For that, I need to apply external electric field, which is called E. So here I am applying external electric field, where external electric field is nothing but it is given as voltage per meter. That means 1 volt per distance. How much voltage you are applying per every distance, that is called as electric field intensity. It is different than voltage. Voltage is nothing but volts, but electric field intensity is different, which is nothing but volts per meter. So it is V by M. So that is equal to, I can write this one as voltage applied per every meter. Voltage applied per every meter, which is nothing but electric field intensity. So here, now I am applying this electric field intensity here for this. For example, here +1 I am applying. E is equal to 1. So E is equal to 1 means E is equal to 1 means that is equal to 1 volt per 1 meter I am applying. So that means here +1 I am applying, here -1 I am applying. So what happens? If I apply +1, then The charge carriers which are present at nearby this distance, which are holes. Holes are always a positively charged particle here. Here this is a positive, this is a positive. Then if I apply plus here, this holes repels with each other and move away from that positive potential. So therefore here, first assume that with the help of this plus 1, this hole repels from here and then moves towards right side. Moves towards right side. While it is moving towards right side, it is overcome by another hole, and therefore this hole and this hole gets collide here. If they collide, what happens is the first hole, which is nothing but this one, this first hole will hit this hole, second hole, and therefore it bounces back towards another direction. So it is bouncing back towards other direction like this. So first hole, now here it is the first hole, now here it is present. So now again it collides with another hole, again it bounces back and moves towards this side. Again it is overcome by another hole here, again the first hole collides with this one, again it bounces back here, again now it is reaching with the minus potential, so therefore hole is attracted towards minus potential, the current is flown like this. Current is flown like this. So here we have understood that hole is been bouncing. Hole is been bouncing with respect to collision with another charge carrier. So this bouncing is called as a drift. This bouncing is called as a drift. And the velocity produced by this drift is called a drift velocity. Is called a drift velocity. Velocity produced by the charge carrier due to drift is called a drift velocity. And the current produced, because charge carrier is moving from this position to this position, that is hole. So therefore hole current exists here because it is moving from one point to another point. So hole current exists here. So therefore as hole current is existing due to drift, so that current is called a drift current. That current is called a drift current. So here we are learning about two important points, which is called as drift velocity and drift current. So due to velocity produced due to drift of the charge carriers from one position to another position, that is called drift velocity, and the current produced due to drift of the charge carriers from one position to another position, that is called as a drift current here. So in this way here, due to applied of external electric field and due to uniformly doped semiconductors, we have acquired drift current here. We have acquired drift current. Now let us see some important equations which are present in drift current, which are helpful for competitive exams. First equation, as you know that drift velocity has been happened in this semiconductor, I can write this one as drift velocity is V. At this V, I can say that it is directly proportional to electric field intensity E, because as I increase electric field intensity, what I must see, previously I have applied only 1, now if I increase E is equal to 2, then again velocity of the hole will be increased, and if I apply E is equal to 3, again it's a lot of repulsion of charge carriers are happened here, so therefore velocity of the charge carriers may increase. So I can say that drift velocity is directly proportional to electric field intensity E. As electric field intensity E increases, drift velocity also increases. So now drift velocity V is equal to mu into E, where mu is called mobility of the charge carrier. Now this charge carrier we are dealing about p-type semiconductor, so therefore it is due to holes, so therefore mobility of holes will be happened here. V is equal to mu p into E, where drift velocity V is equal to mobility of the charge carrier, which is hole, into electric field intensity E, which is a very, very important equation for us. We have got V is equal to mu P into E, where mu P is called mobility of the charge carrier. Mu P is called mobility of the charge carrier or mobility of hole, mobility of holes, and here V is called drift velocity. Drift velocity or drift speed, and E is called electric field intensity. E is called electric field intensity, and we have got an important formula where V is equal to mu P into E. Now, we can able to find the units for mobility here, which is a very important for competitive exams like GATE. We can able to find units for mobility here. Units for mobility mu P is equal to, from the above equation, we can get mu P is equal to V divided by E. That is equal to drift velocity. I already told you drift velocity is nothing but its units are meters per second. Drift velocity is nothing but always it is measured in meters per second. Next, electric field intensity E, which is measured in volts per meter. So therefore that is equal to meter per second into meter per volt. That is equal to meter square per volt second. Meter square per volt second. It can also be written as centimeter square per volt second. If you consider in centimeters, you can write in centimeters. If you consider in meters, you can write in meters. So therefore the units for mobility are meter square per volt second or centimeter square per volt second. Next we have another equation from this. As current is produced in this device, current density also exists. What is that current density? The current density is the current produced for every unit area. For every unit area, what is the amount of current produced? That is called as current density. So I can represent current density here as current density is given by Jp, because I am writing P here. J means current density and it is due to holes, because we are considering here p-type semiconductor. So therefore current density is equal to Jp. So Jp is nothing but it is equal to rho into V. The original equation for current density is rho into V and its units are amperes per meter square. Amperes per meter square. What is rho? Rho is called a charge density. Rho is called charge density, and this charge density can be written as, this charge density rho can be written for p-type semiconductor, it is written as Pe for p-type semiconductor, and it is written as Ne for n-type semiconductor. For n-type semiconductor. Pe for p-type and Ne for n-type semiconductor. So, and V is nothing but drift velocity again. So let us substitute the values here. Jp, current density due to holes, is equal to rho, because we are taking here p-type semiconductor. So therefore I can write this one as Pe, where P is the concentration of holes and E is the charge of that hole. So Pe into V. V is nothing but mu P into E. Mu P into E. So I got an expression again for current density as Jp is equal to Pe mu Pe. This is one of the formula for current density Jp, which is equal to Pe mu Pe. The same thing I can go with I can write this equation as current density Jp is equal to, I can write this one as sigma P into E. Sigma P into E, where sigma P is called conductivity. Sigma P, where it is equal to Pe mu P. Pe mu P, it is called conductivity. It is called conductivity, because sigma P is equal to, I am replacing Pe mu P by sigma P. So therefore formula is Jp is equal to sigma P into E. Sigma P is called conductivity, which is nothing but Pe into mu P. Now let us find what are the units for this conductivity here. Again the same point, units for conductivity. Units for conductivity sigma P is equal to, from the above equation we have Jp divided by E. Sigma P is written as Jp divided by P, where J is called current density, that is equal to amperes per meter square, units are amperes per meter square, divided by E is electric field intensity. So electric field intensity, again what is the formula for electric field intensity? Units are volts per meter. So from this I got amperes per meter square into meter per volt. So 1 meter square cancels, that is equal to 1 divided by meter into volt by A. I am bringing A towards the denominator. So that is equal to 1 divided by meter into voltage by current. It's nothing but voltage by current is nothing but resistance. Resistance units are ohm. So therefore I can write this one as ohm like this. So now this one can be written as ohm meter inverse. If it comes to numerator, so it's nothing but ohm meter inverse. So the units for conductivity are ohm meter inverse. Ohm meter inverse. Now similarly, we have another term here, very important term into consideration here. It is called resistivity. Resistivity, which is given by rho p, that is equal to, it is nothing but 1 by sigma p conductivity. 1 by sigma p, which is the inverse of conductivity. So that is equal to 1 by sigma p is nothing but what? Pe mu p for p type semiconductor. Right. Now again the units for resistivity. Units for resistivity are, units for resistivity is equal to, it is 1 by ohm meter inverse, that is equal to, if it comes to numerator, you have ohm meters. These are the units for resistivity, which is nothing but ohm meter. Right. Again we have another formula, because as resistivity comes here, I am dealing with another resistance, which is another term, which is a special term in semiconductors. There is another formula what I want to express here in terms of resistivity and resistance. So therefore here I can write this one as resistivity rho is given by R A divided by L. This is another formula regarding resistivity and resistance. Resistivity rho is equal to resistance R area divided by L. So resistivity rho is equal to resistance are ohms into area is units are meter square, length units are meters, meter square cancels. So rho is equal to ohm meter. Rho is equal to ohm meter. What we have got here, which is nothing but ohm meter. So this is the unit for resistivity rho ohm meter. We can use this formula also, provided that resistance is given, area of semiconductor is given, and the length of the semiconductor should be given. So this is about the p-type semiconductor, which we are using here in order to obtain drift current here. So these are all the various equations what we have got, starting from drift velocity, V is directly proportional to E, V is equal to mu p into E, again current density, again conductivity, and also resistivity. Okay. Now the similar things can be applied for n-type semiconductor also. If I use n-type semiconductor here, the same formulas exist here. So let us see what are the formulas existing for n-type semiconductor. If I use n-type semiconductor, then the first equation is V is equal to mu n into E, where mu n is called mobility of electrons. Mu n is called mobility of electrons. Next, conductivity Jn is equal to, I can write this one as n E mu n into E. This is another formula for conductivity of electrons. N E mu n into E. N is concentration of electrons, E is the charge of electron, mu n is the mobility of electron, E is electric field intensity. Next, similarly, I can go with the sigma n, which is conductivity, which is written as sigma n is equal to n E mu n. N E mu n. Also, I can write as resistivity rho n is equal to 1 by sigma n, that is equal to 1 by n E mu n by n E mu n. So these are all the equations for n-type semiconductor. If I go over with respect to n-type semiconductor, what we are using here. Now these are all the equations which are existing for a doped semiconductor, that is extrinsic semiconductor, because we are taking this one for p type and also for these equations exist for n type semiconductor. Suppose if it is intrinsic semiconductor, what happens? What is the current density and conductivity and resistivity for intrinsic semiconductor? That is the most important point that we need to learn here. For intrinsic semiconductor, for example, intrinsic semiconductor. What is intrinsic semiconductor? It is a purest form of semiconductor which is not doped with the dopants like p-type impurities and n-type impurities. That is called as intrinsic semiconductor. Now, for intrinsic semiconductor, what is the drift current? For intrinsic semiconductor, the drift current is given by J is equal to, it is a combination of hole current plus electron current. It is a combination of hole current plus electron current, which is nothing but current density. This is nothing but current density, hole current plus electron current. So that means J is equal to Jp, already we have got Jp is equal to Pe mu P E plus Jn is equal to Ne mu N into E. Now, for intrinsic semiconductor, already we know that number of electrons is equal to number of holes, that is equal to intrinsic concentration Ni, that is N is equal to P is equal to Ni. So, therefore, J is equal to, I can write instead of P, I can write it as Ni E mu P capital E plus, instead of N, I can write as intrinsic concentration Ni E mu N capital E. So, J is equal to, for intrinsic semiconductor, we can take out the common terms as capital E and Ni. So, take out capital Ni E capital E. So, which is nothing but mu P plus mu N. This is the current density for intrinsic semiconductor, which is not a p-type and not an n-type. Both electrons and holes mobilities exist here, which is nothing but J is equal to Ni E capital E into mu P plus mu N. Okay. Next, similarly, what is the current density conductivity for this? It can be written as J is equal to sigma E, where sigma is nothing but intrinsic conductivity, and it is given by G sigma is equal to Ni E into mu N plus mu P. This is the conductivity for intrinsic semiconductor. So, these are all the various important formulas that we are learning today. Now, I hope the audience have got a clear explanation about the drift current. Now, let us see the various gate problems that are coming under drift current. The first one, in a semiconductor under high electric fields, with increasing electric fields, mobility of charge carriers dash and velocity of charge carriers dash. So, in a semiconductor under high electric fields, that means electric field is very high. Electric field is very high. It is given in the problem, electric field is very high. With increasing electric fields, under high electric field and also increasing electric field, mobility of charge carriers, what happens, and velocity of the charge carriers, what happens. Okay. So, as we know that from drift current, V is equal to, we have mobility mu into E, formula velocity, drift velocity, V is equal to mobility mu into E, electric field intensity. So, now here, as in the problem, it is said that electric field intensity is increasing. As electric field intensity is increasing, what happens to first mobility of charge carrier? Mobility is given by mu is equal to V divided by E. So, as electric field intensity is increasing, what happens is the overall value mobility decays. So, therefore, as electric field intensity is increasing, mobility decreases. So here mobility of the charge carrier decreases. Mobility of the charge carrier decreases. And what about velocity of the charge carrier? As you know that velocity, we know velocity is equal to, it's nothing but mu multiplied by E. But here what happens, mu mobility is been decaying, electric field is increasing here. Mobility is decaying and electric field is increasing. So therefore for every increment of electric field intensity there is a decrement of mobility here. So what happens, so now the velocity, what happens is it will neutralize. There is no effect for velocity as electric field intensity is increasing, mobility is decaying. So therefore there is no effect of drift velocity and therefore it is said to be in neutralize. It will, drift velocity will neutralize. So here, and velocity of charge carriers gets neutral. Gets neutral. So this is the concept of drift velocity in this problem. Let's go with another problem here. In n-type silicon sample having electron mobility mu n twice the whole mobility mu p. So given, what is given here? The given n-type silicon is given, n-type silicon, and electron mobility mu n is equal to twice that of mobility of holes mu p, is subjected to a steady illumination such that the electron concentration doubles from its thermal equilibrium value. Electron concentration having electron mobility mu n twice the whole mobility mu p, and electron concentration such that the electron concentration doubles from its thermal equilibrium value. As a result, the conductivity of the sample increases by a factor of. So what happens? So he is telling that mobility is been increased to twice that of whole mobility and the electron concentration is been doubling. So from its thermal equilibrium value. So what happens to conductivity here? Conductivity we need to find. Of the sample, it has been increases by a factor of what? Originally, what is the conductivity? Before illumination and after illumination, what is the conductivity? So first write before illumination, before conductivity before. We have a formula for conductivity. Sigma is equal to Ne mu n. Ne mu n, because it's an n-type semiconductor. Conductivity after illumination. After illumination, what happens? The formula is Ne mu n. Ne mu n. But after illumination, what happens here? Twice the whole mobility. So therefore, here mu n can be written as 2 into mu p. That is equal to Ne 2 into mu p. So you get here 2 Ne mu p. Okay, or this one can be written as N p mu p. So sigma after illumination divided by sigma before illumination. It is written as, after illumination can be written as 2 Ne mu p divided by, before illumination you can write this one as Ne mu p. Both gets cancelled. So it is increased by a factor of 2. It is increased by a factor of 2. So sigma after illumination is been increased by a factor of how much? 2. By a factor of 2. Okay. So this is the concept of this problem. Okay. Thank you so much. We'll continue in next class.